Did you know the moon might be holding onto Earth's secrets? Literally? It turns out our planet has been sprinkling the moon with water and other life-sustaining ingredients for billions of years, and this discovery could rewrite what we know about both worlds. But here's where it gets even more fascinating. The moon, often seen as a barren rock, might actually be a time capsule of Earth's ancient atmosphere. New research reveals that tiny particles from Earth's atmosphere have been hitching a ride on the solar wind, embedding themselves into the moon's soil. And this is the part most people miss. Earth's magnetic field, long thought to be a protective shield, might actually be helping these particles escape and journey to the moon. Led by experts at the University of Rochester, this study tackles a decades-old mystery. Why do lunar samples contain more volatile elements than the sun's particle stream could explain? The answer might lie in Earth's own atmosphere, which has been subtly contributing to the moon's composition over eons. Astrophysicist Eric Blackman explains, by combining lunar soil data with computational models, we're tracing the history of Earth's atmosphere and its magnetic field. Since the Apollo missions brought lunar soil samples back in the 1970s, scientists have been dissecting their contents. These grains contain a mix of volatiles, water, carbon dioxide, helium, argon, and nitrogen, some of which clearly come from the solar wind. But the amounts, especially nitrogen, don't add up if the sun is the sole source. Here's the controversial twist. A 2005 study from the University of Tokyo suggested that some of these volatiles might have come from Earth's atmosphere, but only before our planet developed a global magnetic field. The logic: a magnetic shield should prevent atmospheric particles from escaping. But the new research flips this idea on its head, showing that even with a strong magnetic field, particles can escape, and the field might even guide them toward the moon. To test this, researchers ran advanced simulations, comparing an early Earth without a magnetic field to a modern Earth with one. Surprisingly, the modern Earth scenario better explains the particles found in Apollo samples. How does this work? Solar wind ions collide with Earth's atmosphere, knocking loose neutral and charged particles. Instead of blocking them, the magnetic field acts like a rail system, guiding these particles along arcs that stretch tens of thousands of kilometers into space. Some of these particles eventually reach the moon's orbit and settle onto its surface, a slow, steady drizzle over billions of years. If this is true, the moon's regolith becomes a priceless archive of Earth's atmospheric history. Layer by layer, it preserves a geochemical record of shifting continents, volcanic eruptions, evolving life, and even human industrialization. But here's the bigger question. Could this process have implications for other planets? Mars, for instance, once had a magnetic field and a thicker atmosphere. Understanding how these factors interact could help us answer when and how Mars lost its air, and what it takes for a planet to retain volatiles long enough for life to emerge. For lunar explorers, the practical benefits are equally exciting. Earth-sourced volatiles like water and nitrogen could be extracted to create air, water, and fertilizer on the moon, reducing the need for costly resupply missions. Even small local reserves could make a lunar outpost sustainable. So what does this mean for us? The moon isn't just a silent observer. It's been quietly collecting traces of Earth's atmosphere for billions of years, reflecting our planet's story back to us. But here's the thought-provoking part. If the moon holds Earth's history, what other secrets might it reveal about our past and our future? Let us know your thoughts in the comments below.